Hello, everyone. All right. Salutations. I think I'm going to get started. Today's lesson is about rolling. Okay. And in particular, rolling without slipping. Okay. So, what does it mean to be rolling without slipping? Okay. So let me define some variables here. S is defined as arc length. Arc length for a circle. Okay. So let's suppose we have a circle. Okay. Here's the center of the circle. And circle has a radius r. Okay. And let's suppose that the circle rolls without slipping. Okay. So maybe it rolls like this. Okay. And this is the amount. We'll just say that this part right here. So here's the point A. And the point A has rotated over to this spot. Okay. And so now there's a new point that's in contact. And we have some angle theta. And the angle theta subtends a distance r. Okay. The angle theta subtends this arc length s. Now, in the process of rolling, the wheel has moved forward a distance x. Now, if the thing is rolling without slipping, okay, then that means that the distance the wheel moves forward is equal to that amount of arc length. Okay? Okay? Because you can imagine if something is rolling while slipping, it's spinning, but it's not traveling the right amount of distance. Okay? So then we would use the fact that arc length in a circle is theta times r. All right, so that distance is related to the angle. So basically what this equation does right here is it relates angular displacement to linear displacement. So that only happens when you're rolling without slipping. So if you're slipping, then the spinning of the wheel is not related to the amount that the wheel is traveling forward. Okay? But if you're rolling without slipping, then there is this relationship. Okay? Then what we can do is we can take the derivative of both sides of the equation. So we get dx dt equals d theta dt times r, because the radius of the wheel is a constant, so when we take the derivative of that, it doesn't have a derivative. So we take the derivative, we get that. The derivative of position with respect to time is the linear velocity. The derivative of angle with respect to time is the angular velocity. So we have this equation. Okay. Then we take the derivative again. We do the derivative of the velocity with respect to time. Okay. So on the left-hand side, we have linear acceleration, and on the right-hand side, we have angular acceleration. All right? So this equation is the equation for rolling without slipping. Really, all three of these equations, this, v equals omega r, these are all equations that are expressing rolling without slipping. But this is the one we're going to use. Okay. So then we also have our equation for translational motion, which is net force equals ma. All right. And then we also have our equation for net. We have our equation for rotational dynamics, which is net torque equals I alpha. Okay, so these are going to be the three equations that we're dealing with today. So we're going to have a system of three equations. All right. One of the things I want to point out here is the angular displacement in this case. To make the wheel roll in the positive direction, it has to do a clockwise rotation. So we have to be careful about the signs. So I'm just going to put be careful about the sign. Because this is technically a negative angular displacement, but I've written this equation with a positive, as is usually done. So we just got to be careful, and I'll talk about that as we do examples. So basically, I'm going to do two examples that will illustrate how this works, and then we'll go to the Zoom room. Okay. So this first example is a yo-yo. All right. The yo-yo has inertia I. It has mass m. And if we think about a yo-yo, here's the yo-yo, all right? And a yo-yo is basically two discs, all right? This is a side view of a yo-yo. If you were to look at a front view of a yo-yo, it has these two discs, right? And then in between them is an axle, and then the string is kind of wrapped around that and it goes up. Okay? If we were to look at this from the side, here is the center of the yo-yo, and the string is attached right here. Okay? And so the yo-yo is going to unwind this way. Okay? And so what we would like to figure out, oh, by the way, the radius of this inner circle, because if we look at the yo-yo, it's unwinding about this inner circle. Okay? So we'll call the radius of that inner circle, we'll call it B. All right? So let's go ahead and do a so if we think about this in terms of forces, the yo-yo has two forces acting on it. It has the force of tension going up. That force of tension is from the rope, okay, going up, from the rope going up, and it has its weight force going down. So we have the tension is acting right here, and we have the weight force is acting right here, okay? There you have it. Now I'm going to solve this kind of problem similar to a quasi one-dimensional system problem, where I'm going to call downward positive, and I'm going to call clockwise rotation positive. Now, why am I doing that? The reason I'm doing that is because of this equation, A equals alpha R. All right? So notice how if the yo-yo falls downward, then it will rotate clockwise. Okay? So I want to make sure that this equation holds true. All right? And I can see that a downward acceleration will result in a clockwise rotation of the yo-yo. So if A is positive, then that means alpha is going to be positive. All right? So basically what you want to do is you want to think about the system, and the direction that the system is going to move, which in this case is downward, that is, just call that the positive direction. And then the way in which the thing is going to rotate as a result of that motion, you call that the positive sense of rotation. Okay? This yo-yo, it's going to accelerate downward, and as it accelerates downward, it's going to unfurl in the clockwise sense. So I'm going to call both of those things positive. All right? So if I go to my Newton's second law, which says net force equals ma, all right, then I have downward forces are positive, so I have mg minus tension is equal to ma. All right, so that is my Newton's second law equation, linear form of Newton's second law. Now, let's talk about net torque equals I alpha. All right. If we look at this, the weight force acts as if it were going through the center of mass of the yo-yo, okay, which is the center of the yo-yo. So the weight force does not exert a torque. Think about it. If you just had a yo-yo and you just let it drop without the string, it's not going to rotate, right? It's just going to fall straight down. So the weight force does not exert a torque on the yo-yo, all right? But tension does, because it's offset from the center by a distance b, all right? And furthermore, that tension is pulling on the yo-yo and making it rotate in the clockwise sense. So tension is exerting actually a positive torque, because this tension is making it rotate in the positive sense. All right? the size of the torque due to tension is going to be force times distance from the center, so TB. So my net torque is tension times B, and that equals I times alpha. And then I have the equation of rolling without slipping. So in this case, it's unwinding without slipping, but the same idea holds. And I would use, so I have A equals alpha R. But the radius in this case is called B, because there are multiple radii here, because the yo-yo, it has that radius, but then it also has this inner radius, and that's the radius that the yo-yo is actually unfurling about. So I use that radius in my rolling without slipping equation. So I have three equations. What are my unknowns here? Well, the unknowns are the tension in the yo-yo, the linear acceleration, and the angular acceleration. Okay? Those are the three unknowns. Why are those the unknowns and not other things? Because I said the yo-yo has inertia I and it has mass. I said the yo-yo has inertia I, it has mass m, and I said that this distance is b. So those are all givens. So the unknowns are what is the tension and what are the accelerations. Okay? So notice how I have three unknowns and I have three equations. So that's a system of equations that I can solve. So this is our system of equations. Okay? So now I'm going to show you how to solve that system of equations. The first thing I like to do is I like to write normally we're solving for the linear acceleration, not the angular acceleration. So I'm going to eliminate angular acceleration by dividing both sides by b. A over b is alpha. Then I'm going to take that and I'm going to plug it into my Newton's second law for rotation equation. So I have T times B equals I times, and instead of alpha, I'm going to write A over B. And then I'm going to divide both sides by B so that I get tension equals I over B squared times the acceleration. All right. So now I'm going to take this and I'm going to plug it in for the tension in the first equation. So I have mg minus the tension, which I now know is equal to I over b squared times linear acceleration equals mass times linear acceleration. Okay. Might as well divide both sides by m and get g equals, or g minus I over mb squared times linear acceleration equals linear acceleration. I'm going to add this term to the other side. G equals 1 plus I over mb squared times linear acceleration. And then I'm going to divide both sides by this chunk. And so this is going to be the linear acceleration of the yo-yo. One of the things I want to point out is, see how we're dividing the gravitational acceleration by a number that is greater than 1. See how it's 1 plus some positive stuff. Okay? So what that means is that this linear acceleration of the yo-yo is less than gravity. So that's a sanity check, right? Because yo-yos, obviously, if you've ever played with a yo-yo before and you let the yo-yo unfurl on its own, you know that it accelerates downward at a fairly slow rate that's less than gravity. If we were in class, I have these like yo-yos that I've glued on big discs onto the side, so that when the yo-yo unwinds, basically the big discs increase the inertia of the yo-yo, and so and then you can change the inertia of the disc. So we study this relationship in an in-person class, but we don't have the opportunity to do that right now. So maybe if we get back to school this year in person, we will do that lab. So this is a yo-yo. I think that's kind of interesting. Okay. The other thing I wanted to talk about is, so this example is rolling down a hill. Okay. So we have some kind of a hill. The hill makes an angle theta with the horizontal. And we have an object that has a radius r. Okay. And it has inertia I. And it has mass m. Okay? And we want to know, what is the linear acceleration of this thing as it rolls down the incline? Okay? All right. So let's go ahead and calculate it. If we think about the yo-yo, I'm going to do a free body diagram. It has the normal force pushing up on it that way. It has the weight force going downward. And then it has friction. Now, an important point, if you are rolling without friction, then the thing is not sliding against the ground. It's in contact with the ground. Okay? So it is static friction if you are rolling. Okay? Now remember, static friction is not necessarily going to be equal to mu times normal. Okay? Because static friction can be maxed out. So that's a really important point when we're talking about things rolling, because we'll find in this problem that static friction is not maxed out. Okay? So to remind you about inclined planes, we showed that this angle was theta. So if I redraw this free body diagram, we have normal force going this way. We have static friction going this way. We have mg sine of theta going that way. And we have mg cosine of theta going that way. All right? And I'm going to call this direction the x direction and that direction the y direction. So I believe that when I taught this to you guys, I like rotated the paper, but I'm just doing it out. Okay? So I'm going, this wheel or whatever it is obviously going to accelerate only in the x direction. So I'm going to do Newton's second law in the x direction. Okay? So that's my linear Newton's second law. And I can see that my force going down the incline is mg sine theta, and my force going up the incline is static friction. So my net force in the x direction is mg sine theta minus static friction. And that equals ma. All right? So there you go. Then I'm going to look at the Newton's second law for rotation. Net torque equals I alpha. Now, I'm going to sort of zoom in on the wheel. So let's draw the wheel a little bit bigger here. The normal force acts at the point of contact. So there's the normal force right there. We can see that and it's rotating about its center. The wheel is rotating about its center. So we can see that the normal force is actually parallel to the line connecting the point of application of the normal force to the center. Okay? So the normal force has no perpendicular component. Remember, the formula for torque is F perp times R. So the normal force does no torque. Okay? It does no torque because the perpendicular component of the normal force is equal to 0. Okay? Then we have the weight force, which acts through the center of mass. Okay? The weight force also exerts no torque because it is acting through the point of rotation, so it has R equal to 0. So both the normal force and the weight force provide no torque, but for different reasons. Okay? Then we have the static friction force, which is going to act right here. We can see that it is acting perpendicular to this line, and it is a distance r away from the center. So the torque due to friction is static friction times r. Okay? So the net torque, because I have 3 forces and only one of them is exerting a torque. So the net torque is just going to be static friction times r, and that equals I alpha. And then we have our rolling without slipping equation. A equals alpha r. Okay? So we have 3 unknowns here. One of the unknowns is linear acceleration, the other one is static friction, and the other one is angular acceleration. So I'm going to solve this exactly like I did before. So first of all, I'm going to divide both sides of this third equation by r, and I get a over r equals alpha. And then I'm going to plug that into the second equation. So I have static friction times r equals I times a over r. And so what that tells me is that static friction dividing both sides by r is I a over r squared. All right, which I can then plug into the top equation. So I have mg sine theta minus IA over r squared equals MA. I divide this term, or I add this term, excuse me, over to the other side. Mg sine theta equals I over r squared plus m times A. And then I divide by the big chunk, and what I get is the acceleration is g sine theta over the quantity 1 plus I over mr squared. Okay, so notice how it's basically an identical result to the yo-yo. The only difference is that this is on an incline, so we have this, instead of g, it's g sine theta to represent the fact that it's on an incline. We could then plug this in to solve for friction, static friction. Remember, the formula for maximum static friction is mu sub s times normal. So we have obviously not got static friction. We have some other, or maximum static friction. We have some other below the maximum static friction. Okay? So these problems, these are some nice problems. I like these. You get a system of equations. It's a really easy system of equations to solve. So that's my lesson for today. And I will see you in the Zoom room.